Ways to communicate motion. We can communicate motion the following ways. Some are easier to use than others depending on the circumstances. We have a table, a motion diagram, a motion equation, a motion graph. Starting with tables of motion. They're easy to make but difficult to use, as you already saw last lesson. We can make a position and timetable or a velocity and timetable. Position timetable tells us where the object is at different times. Position is positive if the object is going to the right or above the origin. Negative if it's to the left or below the origin. Velocity and timetable tells us how fast an object is going at different times. Velocity is positive if the object is moving up or to the right, and negative if it's moving down or to the left. Here's an example of a position timetable. Note that the times are equally spaced every 2 seconds. The distances become farther apart as the table increases. 0 to 5, which is a difference of 5, then 5 to 20, which is a difference of 15, and so on. The differences are becoming more and more. This means that the object is speeding up because it travels more distance in equal time intervals. The position and timetable shows the exact same motion as the last one. This time, the positions are regularly spaced out, but the times are not. The times become closer together, as you can kind of see without calculating, as the table increases. The first two times are 3 seconds apart, and the last two are half a second apart. That means the object is speeding up because it travels the same distance in a shorter amount of time. So how could we calculate average velocity from a table? Average velocity is going to be your displacement, which is your change in position, divided by the time interval, the change in time. The change in position for the entire table is 36 meters, the difference between 50 and 14.3. The time interval is 2 seconds, 3.1 minus 1.1. Remember, delta is change, and change means final minus initial. Dividing these two will give you 18 meters per second for your average speed. How can we approximate an instantaneous velocity from a table? Let's say we want the velocity right at 3 seconds. Right here, in between these two. Look at the two entries, right around 3 seconds. The change in position is 4.4 meters. The time interval is 0.2 seconds. Dividing these will give us 22 meters per second for the instantaneous speed at the end of the table. Right around 3 seconds. Not exactly 3.0 seconds. You would need other math or more information to figure that out. Here's an example of velocity and time. It's much easier to see that the object speeds up and then slows down because the velocities are decreasing. Each velocity shown is the instantaneous velocity at the time the velocity is paired with. So at 5 seconds, our velocity was 4.32. At 10 seconds, our velocity was 7.68. The problem with finding displacement is very difficult. We can only find displacement between these 2 points on the table because we have displacement equals our average velocity times the time interval. Or, as you have seen it, the speed equation, which is speed equals distance over time, or velocity equals displacement over time. Solving for displacement, multiply each side by t, and we get this. To find displacement between two adjacent pairs, we have to multiply the average of the two velocities by the difference in the two times. Once we find all of the displacements for each possible adjacent pair, we can add them all up to get the net displacement. Here, the sum is 396 meters. You can plug it in if you like, but don't plug it in because it's going to take too long. Suppose we want to change the above position and timetable into a velocity timetable that shows the same motion. To start with, our velocity table is 1 point shorter than our position table because you're adding these two, these two, these two, these two, these two. First point is calculated from the first and second points on the position table. The first velocity is the change in position or the displacement divided by time. From the first and second points, the displacement equals 5 meters and the time equals 2 seconds. So the velocity equals 2.5 seconds, 5 divided by 2. The first time is the average of the two times because the velocity of 2.5 meters per second happened sometime between 0 and 2 seconds. We're not sure on the exact time. So the average of 0 and 2 is 1 second. Second point is calculated from the second and third points, and so on. We're not going to go... There we go. The rest of the points can be calculated following that same pattern. Suppose we want to change the above velocity and timetable into a position timetable that shows the same motion. To start with, the position table has the same number of points and has the same times as the velocity table. The starting position must be specified for us, or else we have to assume that it is 0. And a lot of times that's what we're going to have to do. We're going to assume the starting position is 0, or at least treat it as if it's 0. So suppose that this object starts at position positive 10 meters. Now we find the displacement pair by pair exactly as before. Get the average of the two velocities of the pair, get the time difference, and then multiply the average velocity times the time. Each displacement is added to the previous position to get the next position. Here we started with 10 meters. The displacement adds 10.8 meters to this, so we end up at 20.8 meters. Now we're adding 30 meters to get to 50. Now we add 44 meters, and so on. There it is for you, in case you did want to pause and look at it. Problems with tables, they require a lot of arithmetic work, which is not necessarily hard, but it's kind of annoying, and there's better ways that we can figure this out. It's hard to just look at the numbers on a position and timetable and just know whether the object is speeding up or slowing down. We have to figure out what is happening to the velocity. Is it increasing or decreasing? Is it staying the same? It is difficult to determine displacements and positions from a velocity and timetable because you have to rearrange the velocity equals displacement over time equation to solve for displacement. Changing a position table to a velocity table takes lots of work and is a convoluted process. We don't know for sure what happens between the points on the table. At best, we can just estimate at the average, like we did just a minute ago. We don't know how the object moves during the times before the table starts or after the table ends. Tables are so annoying, so why do we learn about them? When we do an experiment to determine how an object moves, the result of the experiment will always be a position and timetable or a velocity timetable. Since this is all a motion experiment can give us, we need to learn how to deal with the tables.